I'm Angela Desjardins. I'm the principal investigator for the Nationwide Eclipse Ballooning Project. And we're so excited today to have a couple of folks joining us from the Jet Propulsion Lab in California. They are actually going to join us where I'm going to be in Junction, Texas for the eclipse and doing a flight with a couple of engineering payloads and a couple of their own payloads as well. So we're excited to have them join us, and actually we got connected with them as a result of the Olin College team, I think maybe because Jacob is an alum from there. But yes, so they're each going to speak a little bit about what they do at JPL and specifically with the Venus balloon mission. But yeah, so first up will be Jacob Izraelevitz. He has been at JPL since 2017. He got his Ph.D. at MIT, and he is the principal investigator of the balloon design task. And I think he'll talk a little bit about the balloon that they want to fly on Venus is pretty darn cool. And then Siddharth Krishnamoorthy got his PhD at Stanford University. He has also been at JPL since 2017. And he is the lead on the balloon-based seismology task for the Venus mission. So without further ado, yeah, I'll turn it over to, I think Jacob is going to talk first, and then Siddharth will talk next, and then we'll love to have your questions at the end. So yes, thanks.
All right, thanks for that intro, Angela. Do you all see my screen here? Can you still hear me?
Yes.
Yep.
All right, excellent. Okay, so thanks for having us here today. It's a pleasure to talk to a bunch of other balloon enthusiasts. We're very excited about helping you all out during the balloon launches in April. So I'll be talking about the balloon design for our investigation of the clouds of Venus. I am just the front person, though. I'm representing a very large team. There's a lot of folks at JPL helping design these balloons, but also the fabrication actually happens up at Near Space Corporation. They're our primary subcontractor. So for those of you who don't know, Near Space Corporation, they're sort of they're veterans in the balloon business. They're sort of a one-stop shop for fabricating balloons, but also putting payloads up into the stratosphere. They do a lot of flight testing. So it's a pleasure to work with the balloon experts, and then we get to think about the Venus side of it. We also have Paul Byrne at WashU in St. Louis. So he's the science guy for our missions, and he's very much a science evangelist. So you can talk to him about anything associated with Venus, and he's happy to talk to you. Okay. So the story of Venus balloons is actually a relatively old story. And not from our own space program, as it turns out. So the Soviets actually did a lot of Venus work in the 80s. They launched actually 16 landers to the surface of Venus. This is an image of what those landers looked like. Unlike our own normal entry vehicles, their entry vehicles were actually spherical. So this sphere here is the lander, which is sort of funny. And then the rest of this is the carrier spacecraft. So the last two of these landers were extremely ambitious. The carrier spacecraft that delivered it to Venus then went on to go explore Halley's Comet, which is sort of crazy that the orbits worked out for that. And then the landers, as they went down to the surface for these last two missions, they actually launched balloon probes off of the back shell. So this is what those balloons looked like. You can see here it coming down from the back shell and parachute. They inflated and they then flew through the clouds of Venus. Now these were experiment. They were essentially small sondes. They're probes. They're not a lot to them, but they showed that you can fly in the atmosphere of Venus, and it's much more benign than the surface conditions of Venus. Now the surface conditions of Venus are very famously very harsh. It's about 500 degrees Celsius, 90 bar pressure. It's sort of the best analog is the inside of a diesel engine is sort of what the surface of Venus is like. But up the clouds, it's relatively benign. And these balloon probes lasted an order of magnitude longer than the landers did. They're about 3.5 meter diameter balloons, 7 kilogram payload, relatively rudimentary instrumentation. But the winds on Venus were so strong that they actually blew these all the way across the night side of Venus. They survived the Venus day, the Venus sunrise. And they were actually still flying when their batteries died. So as far as we know, they could still be flying on Venus. That's probably not true. But at JPL, we've been thinking for a long time about, okay, so this is a proven architecture. Can we make them bigger? Can we carry modern instrumentation? Can we do a really good investigation of the cloud layer on Venus? Siddharth is going to talk a little bit more later about one of the investigations we want to do, and I'll talk more about the balloon designs themselves. So scaling these balloons up, we call them, instead of a balloon probe, we call them an aerobot. And we call it aerobot because it's a fancy name. It's a robotic balloon-based flying vehicle. And we call it that to make it sound more like a spacecraft, right? We want to differentiate ourselves from the small Vega balloons of the past. And of course, this architecture is relatively proven. We know that the atmospheric density and pressure are relatively similar to sea level on Earth at the altitudes we want to fly. And this means that we can carry mature instrumentation that we already know works at those relatively benign pressure and temperature. Also in the Venus clouds is very convenient. There's plenty of solar power, so you can have relatively power-hungry instrumentation up there, whereas on the surface it's very hard to have enough power to run mature instrumentation. But everything is not perfect in the clouds, right? We like to say they're very Earth-like, but there's a couple of key environmental challenges that make this a little bit hard. The first is that, unlike the stratosphere on Earth, the cloud layer on Venus is a little bit higher temperature. So the top temperature is about 60 Celsius. And this means that we can't just use a standard stratospheric balloon, send it to Venus and expect it to work, right? 60 Celsius is a little bit higher than what you really want to use polyethylene for. There's also, unfortunately, sulfuric acid aerosols. So this is what the clouds of Venus are made out of. They're over 95% concentration, and these acid aerosols will run into your balloon. And if the balloon material is not made out of an acid-resistant material, it will dissolve through the balloon, the helium will come out, and you'll be out of luck. And then additionally, you'll be blown around the Venus planet multiple times in the course of the mission, but you'll be on the dark side of the planet for a relatively long time. And this is a big problem for orbiters, which generally will be on the dark side of a planet for a couple minutes or an hour. We'll be up there for about 70 hours on the night side of Venus. And this means that a lot of your mass has to go towards batteries. And so the investigations you can do on the night side are relatively limited. JPL has been working since the 90s on building essentially larger versions of these Vega balloons. This picture over on the left is a 5-meter prototype. It's called Valor, carrying about 44-kilogram payload. Those folks down there at the bottom, one of them is Viktor Krishnamoorthy, who is actually a veteran from the Vega program who came to JPL in the 90s and helped found our own balloon program, which is great. JPL did a lot of testing of how you deploy these larger balloons, right? The larger the balloon, the harder it is for deployment. Generally, deployment is the largest load. And so JPL did a lot of parachute drop testing of this type of balloon to make sure that once you get to Venus, you can actually deploy it. Now, of course, you could launch from the ground, but one of the big advantages of balloons on Venus is that you don't need to survive the ground conditions, right? So generally, we like to be able to deploy mid-air when we talk about Venus balloons. So I have a video here of what one of those tests look like, and hopefully my sound is still working. So this is a helicopter drop test of one of these balloon prototypes. This was in 2009. So here we are hanging from the helicopter, and as we drop from the helicopter, parachute opens. And now here's the trick, right? We don't want to have this large load of the parachute opening or dropping the helium tanks to snatch the balloon back strongly. So we cheat and we have an external load line that goes outside the balloon, and that load line is what takes a lot of these jerk loads. Once the balloon is fully vertical, then we start putting the helium in. The helium fill should start in a moment here. Oh, sorry, this is cutting the load line in a moment. Here's the load line getting cut. And now we start putting helium in the balloon in a couple of seconds. There we go. Once the helium is in the balloon, we drop the tanks, we drop the parachute, and we continue flying. Generally for Venus, we don't like to carry the helium tanks with us for the course of the flight because it's sort of just dead mass at that point. So any balloon mission is going to be dropping helium tanks onto the surface of Venus. And the Vega balloons were similar in that regard. Okay, So about 6 years ago, we started looking at more complicated balloon designs for Venus. And this is largely driven by the science need. So we want to be able to take our mature instrumentation and not just investigate a single altitude as we get blown around Venus. We want to be able to change what that altitude is, and we want to be able to change that independent of the time of day. So for example, if you want to see a certain layer in the clouds, at sunrise, every time you get blown around the planet, you want to be at a different altitude. So you see how that phenomena changes at sunrise for different altitudes, right? And there's lots of reasons for that. There are gravity waves on Venus, for example. This is what we're looking at for the eclipse. So we've been trying to develop a variable altitude aerobot for Venus with a couple of goals. So first is that now a lot of balloons, so super pressure balloons, which is what the Vega balloons were and what Valor was, are stable in altitude. It's a constant volume. It gets displaced down, it gains buoyancy. If it's displaced up, it loses buoyancy. And this means that you're a stable altitude. If you shut everything off, then the balloon still flies. We want to make sure we keep that. So our variable altitude balloons are still passively stable, but by moving helium between internal chambers, we can change what that stable altitude is. We are still also aiming for long duration. Our materials, we've been doing helium diffusion testing, and we think it's feasible now to have a solar-powered mission that lasts for an entire Venus day. That's 117 Earth days. Balloons on Earth last much longer than that, so it's a relatively reasonable goal. And if you last on Venus that long, you can expect to go around the planet many times. So the winds on Venus super rotate, they go much faster than the surface does. And so you'll get blown around the planet every 5 to 7 Earth days, relatively consistently as long as you enter near the equator. Okay. So here's what the architecture looks like for this type of balloon. It's actually 2 balloons. It's a balloon and balloon design. And we really like this architecture specifically for Venus. So the outer balloon is a zero pressure balloon. And by zero pressure, I mean that the helium inside is the same pressure as the atmosphere outside. It's essentially just a slack bag. And the inner balloon is a super pressure balloon. It's a pressurized reservoir that's constant volume. And by pulling helium between these 2 chambers, we can change our total volume, and so we can go up and down. Now, what's great about this for Venus is that the outer balloon sees the sulfuric acid aerosols, it sees the sunlight, but doesn't see high pressurization loads, so you can use a relatively flimsy material for it. The inner balloon is protected from the acid and protected from the sunlight, but it's under high pressure. And so we can use a very mass-optimized material for that pressurized reservoir, and it's fine if it's sensitive to sunlight, and it's fine if it's sensitive to acid. It's protected from those, right? And so we take advantage of that, right? So the inner balloon in our design is made out of Vectran. It's actually, it's degraded by UV light, so it's nice to keep it in the dark. It's extremely high strength, and it dissolves in acid, but it's fine. It's protected from the aerosols. And the outer balloon is made out of Teflon with a Kapton backing, and the Teflon keeps the acid out. So this ends up, because our balloon materials are very specialized for the different environments, because we've been able to separate those requirements, we can use more optimal materials, we can save mass. That means that we can dedicate more mass to the payload, which means we can get more science. So our technology development program is sort of 3 main thrusts here. On the left, we have balloon and envelope testing. So this is essentially, we take materials that we think can survive Venus, and we actually test them, right? So we do tensile testing with stress testing, we do acid testing of them, we do optical testing to make sure that the radiative heat fluxes off the balloon are adequate, and we also do temperature testing. And some of these we combine. We do combined acid, stress, and temperature testing, for example, for our outer Teflon material. We also do elevated tensile tests of internal materials as well. Once we have balloon materials that we think will survive, we build balloons out of them, and then we go do flight tests. So we fly in the relevant air densities on Earth that are the same atmospheric density and therefore balloon dynamics as where we want to fly on Venus. And we also use these balloon prototypes to demonstrate that we can do deployment and inflation. Our third thrust is we do first principle dynamics models. So we validate those models against our test flights in the Earth atmosphere where we fly, and then we use those models to predict what our balloon responses would be on Venus to Venus conditions by changing the inputs to the simulations, right? So at this point, we've built a couple of these prototypes, 2 of them to date. And as we've been building them, we're getting larger and larger and more payload, and closer to the actual material fidelity we need for Venus. So I'll be talking about our second prototype for the test flights for the rest of the presentation, but we're also currently building our third prototype right now at Near Space Corporation. Caleb can answer any questions on that. He's here in the audience. Essentially, these balloons are made out of the actual materials we want to fly for Venus, and we're getting bigger and bigger and better with them. So our first test flights of these balloons were indoor in a hangar. And this is one of the historic World War II airship hangars. There's a couple of them dotting around the different coasts. This one happens to be up in Oregon. It's the Tillamook airship hangar. And we did 22 short duration slow flights in a still atmosphere. And this is sort of a unique facility that lets you do that. The hangar is 25 stories tall. It's absolutely enormous. So if any of you happen to be up in Tillamook, Oregon, I recommend you go check out this hangar. There's also an air museum in it, and they also use for RV parking. But anyway, it's a very large hangar. It's really great for doing this sort of thing. And the reason we're so careful with these balloons, of course, we fly indoors before we fly outdoors, is that the balloons are extremely expensive, right? We're using the actual materials we want to fly on Venus. And so the balloons themselves are actually much more expensive than the payloads we fly. Testing in the hangar also lets us do deployment tests. So these are some photos from back in 2021 showing the first time we were able to deploy one of these Venus balloons using a crane. Now this is a hanging configuration, which is what you actually need for Venus, the parachute on the top and the payload on the bottom. And we show that this sort of balloon in balloon design, you still can deploy it vertically. So Near Space has since done some more tests under the SBIR program, showing more offloading features and more alignment between the two different envelopes. So more about this at some future day. Okay. But once you're done walking inside of a hangar, you do actually have to go outside and run, have a real atmosphere, real atmospheric dynamics, show that the balloon is altitude stable, all those things. And I have to say that this was extremely successful. This was 2022, so I guess 2 summers ago. We showed that we could do outdoor untethered flights of one of these balloon prototypes. We chose the Black Rock Desert in Nevada for doing these flights. The reason being it's the largest dry lake bed in the United States. And so you can fly for a couple of hours, still land on the lake bed, get the balloon back in one piece and fly it again a couple of days later. So we ended up doing 2 flights. Both of them we were able to execute altitude control, showing that we could change our altitude by 1 kilometer. This is the exact same atmospheric density as 54 to 55 kilometers on Venus, the same densities that we want to be flying at. And the balloon was recovered in good conditions after both flights. We actually are still using this balloon. Near Space has been doing deployment tests on it. So this video is something Paul Byrne put together. Oh, there we go. So let's start this from the beginning. Y'all can hear this video?
Yes.
Hopefully. Okay, excellent. So here's the inflation from the turret. So we had a nice media release on this flight. You can check out more info on it online. All right, but of course it's not enough just to demo that you can fly a balloon. You have to show that you understand its dynamics. And to understand its dynamics, you have to measure its dynamics. And so this flight was actually sort of a Christmas tree of sensors as part of the payload. We're measuring the atmospheric dynamics, we're measuring the atmospheric thermodynamics, we're measuring the balloon internal state, the state of the gases in both balloons, the pressures, altitude, all that sort of thing. And of course, we have to execute control on the balloon, moving helium between these two chambers. And then we're flying in the national airspace. So everything that you need for coordinating with the FAA, we had to do. We had to communicate over iridium and radio. Flight trackers had a termination system for bringing the balloon down in emergency. And this was enormously successful. We were able to show that the flight data from these flights are matching well to our first principle dynamics models. This graph here I'm showing here is from our hangar flight data. We're still working on the paper for the outdoor flight data, but match is still good. And you can see the paper hopefully come out later this year. At this point, we have very good agreement now between the passive dynamics of the balloon and the active dynamics of the balloon and the helium exchange between the reservoir balloon and the outer. Now, the simulation method we use for this is actually a version of what JPL uses for entry simulations for Mars. This is our DARTS code, and it's a sort of a multi-model linked C++ solver, and we have a whole bunch of different nodes for all the thermodynamics of the balloon, the changing of the shape of the balloon, which changes our drag area, which changes how much effective vertical wind we have on the altitude. And all this gets coupled together, and we can use this for simulating flights on Venus now that it's well validated. So this is a graph of what one of those flights could look like on Venus. We're entering here near sunset on the equator, and as the balloon gets blown to the night side of Venus, the altitude is very stable. Our balloon is altitude stable, which is great. On the day side, we have a little bit of superheating of the helium inside, and that changes our buoyancy slightly. We then open up a vent between the two balloons that lets us exchange helium. Our altitude goes up. We tend to spend another night on a different altitude on Venus. We execute another hop as the balloon helium heats up, and then the next day we pump down the helium or get to go to a lower altitude. So this is just one example flight. We can now use this code for simulating lots of different mission scenarios. We can also use it for tweaking balloon designs to make sure that we can hit all of the different environmental constraints. And so this is sort of the next phase of the project, is looking at, now that we have balloons that we know we can build and we know we can fly them, we have good tools for modeling those balloons. Now we can actually simulate what missions look like, and we can use that to start talking with scientists about where they want to fly on Venus. So this is my last slide. We've built a couple of these prototypes. The most recent one, we've been able to show altitude control outdoors over a dry lake bed. We've been able to build these balloons out of Venus-compatible materials and show that those materials are compatible with the sulfuric acid and the temperature. We've been able to show that we can inflate these balloons like you would from a parachute, from a vertical configuration. And now we have good first principle simulation models that we validated against the flight test we've applied to Venus. And of course, next steps, we're building larger balloons, we're doing more dynamic deployments. We're also looking at flying wider altitude ranges. And that's my last slide. So with that, I'll hand it off to Siddharth for the second half of this presentation, and then we'll have questions at the end. So thank you all.
Thank you, Jacob. Sure. So Jacob's mostly talked to you about the vehicle that gets us to Venus. I'm going to talk to you about one of the science investigations that we want to do at Venus, which is infrasound seismology, and I will explain all of that. Before I begin, just want to acknowledge all the contributors and team members in this project. This is a multi-institutional effort that has spanned basically longer than I have been at JPL, which is about 7 years. And so there's a lot of people who have been involved over these years. And so this is just a quick acknowledgement for their efforts. Some of them are in the audience today. So here's an outline of my talk. I'll give you a brief background on what infrasound means and what we do with it on Earth, and how that translates to performing seismology on Venus. This is a balloon-centric crowd, so I've focused this talk more on the different ballooning platforms we've used to perform this work and the kinds of results they've generated. So I'll talk to you about tropospheric, stratospheric, and long duration campaigns, and then motivate a little bit of future work from our results. So on Earth, So first of all, what is infrasound? It is acoustic waves under 20 hertz. So it's the opposite of ultrasound. So it is also inaudible to human beings. And these are low frequency waves, and they travel for long distances without attenuation in the Earth's atmosphere. Several different natural and anthropogenic events produce infrasound. And for that reason, this is used by the Comprehensive Nuclear Test Ban Treaty Organization for nuclear non-proliferation verification. So so they have these arrays pictured here. There are about 15 meters in scale at various distributed along the globe at various points, and they're used as one of the ways in which the CTBTO verifies the absence of nuclear bans. So one of the big things here is that the reason this needs to be 15 meters is because on the ground there's a lot of wind noise, and this is the way they cancel out wind noise by adding a lot of channels so that the signal stands out and the noise dies down. So this plot below shows you how noise drops. So the red line is ground and the blue is a sample noise curve from the stratosphere, and you see that there's almost a 2 to 3 order of magnitude drop. And that's for two reasons. One is that the stratosphere of the Earth is generally a very quiet place. But the more important reason is that when there's wind in the background, the balloon just drifts with the wind. And so you don't actually get a lot of wind noise because you're floating with it. The floating with it is also just tie into the Eclipse project is how you're detecting gravity waves, is that the balloon will experience deviations with the wind, and that's how gravity waves typically get detected on balloons. So Jacob's already done a history of this. I'm not going to spend much time here except to say that we've done these are both artist impressions from Paul. As you can see, the number of times Paul has been mentioned in these two presentations. He's a very good artist, aside from being a great scientist. So we get a lot of good visual effects from him. And so the idea is that the next generation of the aerobot, as Jacob said, is able to carry a lot more mass and is able to change altitude. One of the things that I think perhaps that I would add to what Jacob mentioned is that unlike landers on Venus, which will require individual entry aeroshells to put a lander in a particular location, a single aeroshell can actually deploy multiple balloons on Venus. And there's so much wind shear on Venus that if on the way in you deploy a balloon, say every few kilometers, so say you deploy 3 of them, in a few hours, they've actually separated out by hundreds of kilometers. So you actually have a easy network deployment when it comes to balloons. A little bit about Venus interior and seismicity. So we've actually never performed direct seismology on Venus, and this is for a reason Jacob already mentioned. The temperature and pressure are far too high to allow for long-term survival of instruments on the surface. But what we have seen in radar images is evidence of active volcanism. This is a fairly recent result from last year. There are about 85,000 volcanic structures on the surface. There are also tectonic structures. And we estimate that the seismic activity level on Venus is somewhere between that on Mars, which we've already measured, and on Earth, which we've already measured. And the reason you want to do seismology is to study the interior, which then ties into the evolution of the planet and then ties into the evolution of rocky bodies in the early solar system. So because doing this from the surface is hard, what we do here is we use infrasound, and infrasound utilizes the coupling between the solid planet and the atmosphere. So when the ground shakes, it shakes the atmosphere above it. And on Venus, because the atmosphere is so thick, 90 atmosphere was what Jacob mentioned, the coupling is actually 60 times stronger. So if you had the same size of quake at the same depth with the same faulting mechanism on Earth, it would generate a signal that is 60 times stronger on Venus than on Earth, because this coupling is actually so good. And infrasound travels long distances without dying out. And so you can actually have barometers on balloons that pick up these acoustic waves. And the key thing about barometers on balloons is that they can survive for much longer than seismometers on the surface, because as we mentioned before, the temperature is about 0 degrees Celsius, the pressure is about 1 atmosphere. So if you survive the acid, which we already have discussed solutions for, you can actually survive for a much longer period of time. And seismology is essentially a waiting game. So the more time you have, the better it is. And this I've already mentioned, that you can also deploy a network, and seismology actually benefits from network science. And so therefore, doing this from a balloon confers several advantages. So we also have, like Jacob mentioned in the last talk, have three distinct directions in which we push. One direction is, of course, to show that this signal exists and can be detected from balloons, which is majority of the rest of my talk today. But then the other things that we're working on is being able to automatically figure out that we have seen a signal from a seismic event on the surface of Venus, and to be able to tell it apart from background noise and then tell apart different kinds of signals. And then also to actually miniaturize the sensor so that we can fit all of this within the constraints of a Venus balloon mission, which has limited mass, power. You want to minimize your deployment complexity, and also you cannot send everything back that you record. And so you have to find a way to compress the data that you're recording. So we've done a bunch of campaigns in the last 7 or 8 years. So I'm just going to quickly walk you through different ones. So these are our tropospheric campaigns. So we first started with a seismic hammer, and the seismic hammer produced repeatable signals by hammering the ground. And we had balloon-based barometers close by, so about 200 to 300 meters. And they showed us that this signal was detectable and that we could do direction of flight analysis and be able to geolocate the source on a small scale. Then we went to a larger scale, and we went to, I'm going to wait for this. I didn't want to talk over that. We went to subsurface explosions, and so you put much more energy in the ground and you start seeing different seismic phases come off of that. And so what we found here was that we could use time of flight to distinguish different kinds of seismic phases. And so this was also a slightly larger scale, so 300 meters away. So then we went to 2 kilometers away, but these were still tropospheric flights. Then we did stratospheric flights. And so one kind of stratospheric balloon we use is this solar balloon called the heliotrope, which was designed by Danny Bauman at Sandia. And these balloons actually don't need any helium. So you can fill them up with air from a fan, and the skin is darkened. So the sunlight falls on it and heats the air inside, and it gives you a little bit of lift capacity. So we actually attached barometers to these, and then they'll fly. These are zero pressure balloons, so they actually fly all day and then come down at nighttime. And with these, we were able to do some really cool things. We detected a buried chemical explosion about 54 kilometers away, but also 20 kilometers above the surface. And this experiment was in 2019. And shortly after that experiment, we had this big earthquake in California, which had a lot of aftershocks, and we flew these balloons in the aftermath of those earthquakes, and we got our first detection of a natural earthquake from a balloon. So this was a magnitude 4.2 earthquake. The balloon was at about 16,000 feet, or about 5 kilometers above the ground, and about 80 kilometers away from the epicenter of the earthquake. So this was a crazy result at the time. It feels less crazy now that we've seen other things, but this was the very first time in an uncontrolled setting we flew an instrument. So this is getting close to how we would want to fly it on Venus. Put an instrument on a balloon, and an earthquake happened, and we were able to actually see the earthquake. So that was a really great experience for us. And then we did a campaign in Texas and Oklahoma in 2021 and 2022 to pick up earthquakes from fracking. So this video you're seeing here is a very difficult launch day that I'm extremely impressed by the team that achieved this. This is we worked with students from Oklahoma State University, and this is still a solar balloon, but this is a different launch mode that we use when the winds are too high. As you can see, Zach there, like really struggling with that helium balloon. But what happens is that this helium weather balloon tows up the solar balloon, and then when it reaches altitude, that tow balloon bursts and the entire arrangement falls through the sky and gets ram inflated, but then by then you're above the clouds and the wind is not a problem. And so then this thing continues to float for the rest of the day. So another thing that feels kind of wild that this works, but it actually does seem to work. And on these balloons, we also have two instruments, one separated by 30 meters. And the reason we fly that is because we can do direction of flight analysis. So imagine a wave coming from below. It hits the lower instrument first and it hits the upper instrument next. And you can use the time difference of arrival to actually figure out the direction in which this wave came from. So we did this campaign in Texas, and we actually detected the weakest earthquake we have detected so far. So we detected a magnitude 2.7 earthquake about 22 kilometers away, and this was at about 60,000 feet or 18 kilometers above the surface. And this is kind of what the signal looks like. So these plots show you the signal. The dotted green line is when you expect the signal to arrive given the location of the earthquake. And so you can see that the experimental truth agrees pretty well with the model there. So this is a regional scale experiment. So this one and the last one, so you're about 20 to 100 kilometers away and you're picking up weak earthquakes. But we've also done stratospheric balloon campaigns for different reasons. So this is one of them. This is our campaign that Sandia led with Raven Aerostar. And so what we were testing here was that, can we use, instead of two barometers on a tether, can we use the motion of the balloon in response to the pressure wave as a direction of arrival discriminator? So if you imagine that the balloon reacts to the pressure wave by oscillating in the same direction as the pressure wave, you can actually invert using an IMU the direction in which the wave is coming from. And the main advantage here is that then you don't have to deploy a long tether with a second barometer underneath it. And so it reduces your deployment complexity. So what we did here was we conducted some surface chemical explosions at this area that's marked source. And then we used the balloon IMU and pressure data to try and invert for the direction over the course of 6 explosions. So 1, 2, and 3 are sets of 2 explosions each, and the cones point towards the direction that we inverted. And so we see, at least up close, it does pretty well at inverting for the source. Once you're a little bit far away, the signal to noise ratio becomes pretty low, and this actually becomes kind of hard to invert for the direction. So that's something that we've tested in the stratosphere, but we've also tested continental scale earthquake detection. So this is from our collaborators in France, where they had these sensors on a super pressure balloon that was doing a circumnavigation of the planet. And we had 4 balloons pick up a magnitude 7.3 earthquake. The furthest one was about 2,800 kilometers away. So I just spent some time talking about detections 20 kilometers away. These are detections from 2,000 kilometers, 2,500 kilometers away. Of course, the earthquake is much stronger, but these show you the end members of this detection technique. In addition, during this flight, we also picked up a signal from the famous Hunga Tonga volcanic eruption. So these flights ended up being extremely useful. The other thing that these flights showed was that we can use sensors that are made for engineering purposes. So the sensors that picked up these signals were actually used for altimetry and navigation and balloon health. And they were just sampled faster to produce a detection. So the investigations we're doing are very complementary to atmospheric science investigations, but also to spacecraft, to aerobot navigation. And so that's a really good advantage, because then you don't have to have an instrument that's specifically made for this scientific goal. You can actually piggyback off of some other data, just sampling differently. This is our most recent stratospheric balloon campaign. This balloon also made by Neospace. This is a zero pressure balloon, and we're actually flying one of these balloons during the eclipse. And these balloons and Venus made an appearance as we were inflating this balloon. And this was a very exciting campaign that we did in September of last year when the OSIRIS-REx asteroid sample return mission sent back its sample return capsule through the Earth's atmosphere to land at the Utah test and training range. As it passed over Nevada, this sample return capsule was expected to produce a strong pressure perturbation. And so we flew 2 of these zero pressure balloons and a combination of other solar balloons and weather balloons underneath the re-entry path. And when the spacecraft, the sample return capsule re-entered, we had about 8 balloons in the air, and all 8 of them, and I'm showing a few of them here, all 8 of them picked up this excellent N-wave signal from the air. And so this is the first capture of a bolide-like signal. So this for us, the value here was that this looked like a meteor coming in, which could be Venus relevant. And so we picked up our first Venus relevant bolide signal from a balloon in this activity. What was also interesting, and this is something that only signals that come from above the balloon do, is that we not only picked up the signal from the re-entry capsule, but that signal went to the ground, bounced off of the ground, and came right back up. And then we picked it up a second time, which is shown here in green, about 120 seconds later. So we picked up the downgoing signal and the upgoing signal, and we had 2 barometers on a tether on some of these balloons, and they very clearly show the difference between the signal coming from above and the signal coming from below, which is sort of the point as to why we have those, we have that kind of sensor arrangement. We've also done long duration balloon campaigns. Often NASA sends up these telescopes that float in the air, float very high above the Earth's atmosphere for 7 days, sometimes even 100 days. And we often contribute instruments. So here, this is a flight from 2018. You can see, and with those red tags there, that's our instrument. That's a piggyback. And what this long duration data gathering does is it allows us to accumulate signals of opportunity that might be Venus relevant. So we've picked up infrasound from lightning and thunder. We've picked up infrasound from mountain waves. We've picked up infrasound from the ocean colliding with ice. So there's all kinds of crazy phenomenology that's going on high above us that we're able to capture from this very low noise platform. So we always do this. I mean, balloons in the air all the time is the best way to gather some of this data for us. And so we also partner with NASA to do some of these very high altitude, long duration balloon campaigns. So this is a summary of everything we've picked up in the last few years. So we have our earthquakes ranging from magnitude 2.7 to magnitude 7.3. Distances ranging from 20 kilometers to 2,500 kilometers. We have volcanic eruptions, mountain waves, lightning, and now we are freshly captured bolide signal, which is from the OSIRIS-REx capsule. So I should say these are the signals we've recorded that are Venus relevant. People have recorded a whole bunch of other things, like including airplanes, etc., that we'll be very surprised if we find them on Venus. So we don't really look for those. We're looking for geophysical signals. So the balloons have really helped us in many ways on very many different platforms. So to conclude, what I just said, balloon flights at different altitudes for varying durations ranging from a few hours to like many days have really helped advance the infrasound seismology for Venus. And we use these data to validate our simulation tools, and then we forward model these. We hope to forward model these signals towards Venus. And the more data we have, the better classification we get. And so what this can enable is a way of performing seismology on Venus that is, that is independent of the need to survive at high temperatures and high pressures. And that's like a really good enabling science. But the key thing here is going to be being able to tell that signal apart from everything else that we will hear on Venus. And that's kind of our next challenge. And again, the more data we have, the better it gets. So what we have to do is get from the top picture to the bottom picture. We've more or less finished with the demonstration phase where we've shown every kind of signal that could exist on Venus is able to be captured on a balloon on Earth. But now we have to work on the techniques that identify these signals without ground truth and autonomously. So we've just begun the work on that. So with that, I think I will stop, and Jacob and I can take questions. Thank you.
Hey, it's Kim. I have a couple of questions, one for each of you. First one's a bit of a confirmation of something I heard perhaps 30 years ago, and I don't remember who told me this. But they told me that when you're flying up in a balloon, a person is flying in a balloon, they can hear voices from the ground very clearly. And the explanation was that because the sound wave is moving up from higher density to lower density air, the amplitude sort of amplifies, a bit like when you send a wave down a tapered whip. You know, as the whip gets narrower, it flicks harder. Can you confirm that? Because I have no way of knowing that.
I can't confirm that you can hear people on the ground from any altitude, but most of what you said is accurate in that. There is conservation of energy in the pressure wave as it's traveling up, and so it does amplify, but there's also geometric attenuation. So you know, your wavefront is becoming larger, and so your experience of sampling it at a point may vary, but the thermal structure of the atmosphere is such that it is naturally curving. If you do Snell's law and you plot acoustic rays, they are naturally focusing the transmission upward.
Very interesting.
Because how the temperature lapses near the surface. And the other thing is, of course, like it's very quiet on a balloon. So if you've been on a hot air balloon, it is remarkably quiet because of this floating with the wind phenomenon, right? So your wind relative velocity is so low that the RMS pressure fluctuation from the dynamic pressure of the wind is actually very, very low. So that kills the background a little bit.
Just wanted very cool measurements that you've done. I had no idea that you could get all that information from barometers hanging on.
Yeah, it was exciting. I didn't know about this till I got to JPL, and so I was very happy to have been inducted into the Church of Infrasound.
So, Jacob, this is a shorter question. Any reason you're not using hydrogen on Venus instead of helium?
Yeah, so hydrogen works on Venus, you know, just like it works here. The mass gains you get from hydrogen versus helium, though, are not as it's not as worthwhile on Venus. So it's a carbon dioxide atmosphere, and so the difference in your molecular masses means that it's not quite as big of a win as you might expect.
And
really,
that's
the issue
reason,
is
it's more to do with the diffusion, the helium diffusion.
That's also fair. That's also fair. Yeah.
That was the real reason I was wondering.
Yeah. But we also have, from a testing logistics standpoint, you know, since we do want to fly balloons, we want to be able to capture the dynamics. And because we are JPL and we are extremely safe with everything we do, the logistics hurdles of doing the flights with hydrogen versus helium means that if you go the helium route, it's a lot easier to do the testing. And so that saves us costs.
I get that. For Earth-based testing, I totally understand that. But how about for the actual mission itself? You understand the differences well enough that you could fly hydrogen tanks instead of helium tanks?
Yeah, I mean, the diffusion problem gets different, right? So you would need a different envelope design. So it actually ends up being a relatively early choice.
I see.
Okay,
so it's not just diffusion is slower because it's diatomic versus monatomic. It's actual material compatibility too.
Yeah.
All right, thanks.
So you have hydrogen embrittlement and that sort of thing.
Right, exactly. So it was a longer question than I thought. Okay, thanks.
No, it's fine. Any other questions?
I have a quick one, but it's not pertaining to the presentation. Jacob and Sid, you guys both did so well, but I was wondering if after we're done with the questions, if folks could, I wanted to give people a little bit of heads up warning, if folks could show their camera on and we could take a screenshot for a group photo, that would be fantastic from the JPL side of things, if folks want to participate. But I know you generally need a heads up, so this is that early warning, but we can go back to normal questions.
I didn't think to turn on my camera when I was asking the question, but I'm happy to do so. You can enjoy my nuclear launch facility behind me.
I'll
We did have,
folks.
oh,
Oh, go ahead, Julia.
sorry, Jackie. I was just going to say, we do have a question that was submitted ahead of time, and it was basically from students asking if we could get some more information on what they could do or learn right now in their education and life to help improve their chances of working alongside these amazing people. So typically we ask if the speakers are comfortable sharing their contact information, if any students want to reach out to them directly or mention anything they know now to kind of help improve engagement.
Sure. So, I mean, I'm happy to send, feel free to distribute my email. That's totally fine. We do like balloon enthusiasts. Yes. So, yeah, but, we do hire at, all different levels within the lab. So, bachelor's up through PhD. It's about a third in terms of distribution of, at least on the engineering side of what sort of degree level folks are at. A lot of the and at JPL we do both research work. So Siddharth and I are mostly on the research side of things. We're working on developing missions of the future. There's also folks that are working on missions that are currently in flight, including design of actual spacecraft and also flying them once they are in orbit. So we do the full spectrum at JPL.
So I have kind of a follow-on question to that. So, maybe you all aren't the ones, hiring new people that come in, but say you were, how important is it, do you think, for the incoming people to have some experience with ballooning or the types of experiments and things that go on balloons? Is that of interest?
Yeah, I think I often feel this. I think people may disagree with me on this, but I find that in spaceflight, you're fundamentally doing a lot of things that you did in school, but just very, 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 very reliably, because it's all built with the mindset of there's no repair possible. And I think for me, like the biggest learning there has been experiential, in that I think I used to do things a certain way in grad school, and when I look back at it, after coming to JPL and like working alongside people who've been doing like mission work for like 20, 25, 30 years, they would just think of things that could happen that would not cross my mind at all. And I feel like that's a very learned art. And this is an organization that's very, at least in the mission space, very focused on like lessons learned and not repeating the same mistake again and just being very careful. And I think that's it's a very valuable mindset. And so, like, to go back to the earlier question of sort of what should students be doing, I think I've found that what your degree is in, or like what you've done, seems a little less widely relevant than sort of your skills to pick up new things and sort of learn and adjust from mistakes. And so that for me has been sort of the biggest learning here. So yeah, but prior experience, any experience is always, I think, very beneficial. Yes. And sorry, just to add, we have two students here who have worked with us on balloon things, and so like maybe once Jacob is done, they can talk about how things changed for them after sort of doing balloons the NASA way versus the school way.
Jacob, you are muted.
Oh, sorry.
Not that Jacob. Jacob Morgan. It looks like he's talking.
No, I'm so sorry. I'm kind of just geeking out with a friend right now. She's
Well, that's awesome. I'm geeking out too.
Yeah, we've been listening to you guys talk about this, and it's an awesome experience. So thank you again for sharing with us what you're doing. And yeah, I'll let you guys continue.
In the chat, Jackie said she wanted to let Jacob and Sid answer, but I'd like to respond a little bit on the hiring question. So I've hired many people at JPL and interviewed many more. I'm not a hiring manager right now, but I've still done a lot of interviews. and at least on the mechanical engineering side, because that's where I reside, we really value the hands-on experiences, the internships, if you've, in this case, ballooning, if you've gone out and launched balloons, that would be awesome. But that, if you've had a senior project where you were the team lead or something like that, those kind of experiences count a lot more than a 4.0 GPA. It's nice to have both, but the hands-on experiences are really valuable when we're considering hiring people. So go look for those opportunities.
Wonderful. Any other questions before we, turn our cameras on and do a screenshot group picture?
Angela, I just had somebody come into my office, so I missed like half the questions. But I have a question, so hopefully it's not already been asked. So I do a lot of ballooning with students, and I think it's a really cool way to learn science and engineering. I guess I'm curious if you guys see ballooning as something that, I know it's been happening for a long time, but is it in terms of a career path, like something that's growing, like rocketry is right now, something that's kind of staying steady or decreasing? Like, what do you see the future of a student that has a lot of experience in ballooning? I mean, like,
Well,
it's a hard question.
no, it's fine. I guess I'll say so. We're all balloon enthusiasts here, right?
Yeah.
But ballooning is a relatively small part of what JPL does, right?
Mhm.
So, we sort of have, a small group of, maybe 15 or so people that go off to their, day jobs within JPL. And then once we get a balloon project up and running, they're all like, oh, drop that other stuff. Let's go do balloon stuff again because it's so much fun.
Yeah.
So
It's the most fun part of our job, I will say that.
it is the most fun part of our jobs, yeah. But it is growing, right? Our funding within JPL comes and goes, right?
Yeah.
But I think also talking about ballooning as a career outside of JPL, like I think, it is near space access. I think is growing in that, like if you don't necessarily have the funds to like procure a launch vehicle and put your payload in space, but it's able to work at 30-35 kilometers. In the education space, but also in the industrial space. I mean, I guess Caleb is still here. They work with a lot of industrial partners on doing these experiments. I think there is a lot of space for people to get involved, and I will also say that I think the skills you gather are very transferable to proper space or other areas, because a lot of what we do in our experiments, like I mean, I did the instruments for that flight you saw the video for, is electronics and avionics, and like you can apply that to like various different things. There's material science, there's mechanical engineering, right? There's thermal design. So these are very sort of fundamental engineering and science skills that are very widely applicable. So even if you don't continue to work in ballooning, you can sort of take those skills elsewhere. I think so. It's a good place to. It's a very good proving ground for some of these challenges, I think.
Yeah, and it's an excellent way to get field experience very early in careers, right? So I'm actually in a robotics group. Jackie's my boss, actually. Runs Extreme Environment Robotics, and we really value, we are an industry group that does robotics, right? So we're a lot more into the practice of robots than the theory of it, right? And what this means is that we design systems and we take them out to the field and we make them fail there, right? And so having that experience in college is really fantastic, right? It's coupling the design of the system with the field logistics. It's really great.
Great, thank you.
Well, I think we're out of time. Definitely want to respect everyone's time. So yeah, anyone who wants to turn on their camera, we can do a quick screenshot.
Everyone look towards where your camera is.
A quick question, are the slides going to be available from today?
Yes, I'm gonna post this recording on the NEBP Speaker Series YouTube page, and then it'll also be on the NEBP speaker series website, which I'll put in the chat in a second.
Okay,
Zach, are you launching a balloon?
I was gonna say, Zach, are you all like doing a campaign?
Drone boo.
I'm sorry. We're testing advanced air mobility vehicles out here today.
We only get excited when it's lighter than air. Sorry.
I'm sorry. I got some projects waiting for some funding, but no, today is drone day.
Great. I'm going to go ahead and do the countdown. So if you could please look at your cameras in 3, 2, 1, smile. Okay, I took a few. All right, thanks, y'all.
Wonderful. Yeah, well, thanks so much.
Nice job, guys.
Yeah. Thanks so much, everyone at JPL, for the super interesting talk. Yeah, especially Jacob and Siddharth. That was really super interesting. I was totally glued to what you were saying, and I'm thinking of all these different groups. It'd be great to have you talk in. But first, we have to do an eclipse in 13 days, and
we'll see some of you there.
Yeah. Yeah. So Siddharth and I and Tanya and Jackie are going to be in Junction, Texas. So.
Oh, wonderful! It'll be so great. I'll be in Junction too. It'll be great to meet all of you in person and do some ballooning.
All right. Thank you, everyone.
All right. Thank you.
Bye.
All right, thank you.
Thanks, Jacob.